In this video lecture, we'll discuss the basic ideas of one-dimensional arrays in programming and why we need them in the first place. Okay, let's get started. To give you some motivation for 1D arrays in programming, consider the following example. Let's say that we're a weather reporter or a climate researcher and we needed to calculate the average temperature in a certain city over the course of 1 year. For example, here in the Sacramento area, we might have some daily average temperatures that look something like this: chilly at either end of the year and hot in the summer around my birthday. So obviously this problem will involve averaging 365 daily average temperatures, assuming a non-leap year. One approach, as we see here, would be to treat each piece of data as one individual double variable, or what we call a scalar value. Then we'd simply sum up all 365 values, divide by their count, and obtain the desired average result. While this is one completely acceptable and accurate approach, I think we'll quickly realize that this is a very painful and inefficient approach. We'd have to name, declare, and initialize 365 individual double variables to do this, not to mention typing them all up in some colossal summing statement. Would you want to do it this way? I know I wouldn't. Isn't there some better way of doing this? Well, in any modern programming language such as Java, of course there is, and that way involves what we call arrays. So, what is an array? An array is simply some named, ordered sequence of variables or objects, all of the same data type. The elements of an array can be any one of these types: variables of any of the 8 primitive data types, objects of any class type such as strings, CS12 dates, or dams, or even other arrays themselves, which leads us to 2D, 3D, or higher dimension arrays. In this course, owing to time constraints, we'll focus solely on 1D arrays for now. The beauty of arrays is that they allow us to refer to some collection of related variables in an aggregate way, using one common name, and using numerical indexing. The key point here is that every element of any array is of the same data type. The manipulation and traversal of arrays is done using for loops. Hence, arrays and for loops are very tightly coupled, which of course is why we cover for loops in advance of covering arrays. An array has a parameter available such that it knows its own size, which makes a count-controlled for loop ideal for navigating an array, as we'll see shortly. So here's a nice diagram I found online which depicts the 3 key aspects of a 1D array. First of all, an array is similar to what we've already seen with strings and objects in general, in that we declare and use an array using an array reference, shown here in green. An array reference is simply the name of the array, but in reality it's like a pointer to somewhere else in memory where the actual array data is stored. Each piece of data in an array is called an element of the array, as we see here in red, and all the elements of an array are stored contiguously in memory. So for example, if this is an array of integers, there are 4 elements in this array, and each one of these 4 array elements represents one distinct integer value. Finally, each element in this array can be accessed by what we call its index, which is simply its relative numerical position within the array. And these indices begin numbering up from 0. So we say arrays, like strings, are 0-based in Java. So in this diagram, this would be element 0, element 1, element 2, and element 3 of the integer array called test scores. And again, every one of these elements is one individual int value. By the way, that name test scores with the underscore is not in keeping with our usual camel case naming convention for variables. But again, this is just a diagram I found. Hopefully this looks a little familiar to you from when we took a look at strings, because it's a very similar idea. Remember that for strings we had a string reference and a collection of individual chars which we could individually access by their index within the string using the char@. method. We'll soon see that the mechanics of an array are slightly different, but it's a similar fundamental idea. Finally, why and where do we use arrays anyway? Arrays are a common programming component in countless standard applications. They are often used to perform the same operations on long lists of like-typed items. You'll find arrays frequently used in all kinds of bulk data processing applications such as these: mathematics, graphing, graphics, simulation, digital signal processing or DSP, image processing, statistics, and so many more. Arrays help us operate on large amounts of data using a compact syntax. Arrays free us up from having to create and maintain countless individual scalar variables when handling large amounts of data. For example, it would be massively painful to sum up 1,000 test scores if we had to do it like this and give unique names to every score. But it's a trivial 3 lines of code to do it using a score array and for looping from 0 to 999. Okay, now that we have a basic understanding of what arrays are and why we use them, let's start looking at the mechanics of using 1D arrays in programs.